We're going to go through a few concept questions here. These will be specifically related to standing waves on a string. So please answer the question first on your own. Even if you're not positive, choose an answer and then watch the solution. So here is our first question. What do you think about this? So the correct answer here is B. Now the reason this is in the section on standing waves is when we pluck a guitar string, this string itself vibrates back and forth in the fundamental mode. So it looks like a loop in the middle. It's not that exaggerated, but a loop in the middle and fixed at both ends. Now, in terms of the wave speed, we know the speed of a wave on a string is equal to the square root of the force of tension and inversely related to the linear mass density. So they're telling us these strings are the same length. They're under nearly the same tension. So we'll just say this tension is the same. And ultimately, they differ based off of mu, this linear mass density. Since mu is the ratio of mass per length, a thicker string has more mass. So it has a larger linear mass density. The thinnest string has the smallest linear mass density. Since mu's in the denominator, the smallest value is going to give us the biggest speed. And that's why the thinnest string plays the highest notes. Since speed is wavelength times frequency, the wavelength's always related to the length of the string itself. A higher speed is going to correlate to a higher frequency that the string oscillates at. And as it vibrates and oscillates back and forth, it's pushing on the gas molecules, which in turn is creating the sound wave that travels through the air at a speed that depends upon the temperature of the air. Let's look at another question. The correct answer here is B. There's a couple ways to go about this. If you remember the fundamental, mode 1 is one loop. And then mode 2 was 2 antinodes or loops. Mode 3 would be 3 antinodes. Mode 4, so forth, would be 4 antinodes. We can simply count these antinodes. There's 5 of them. That means this is mode 5 or harmonic number 5, the 5th harmonic. The other thing we can do is use the generic equation that tells us that wavelength of the mth harmonic is 2L over m, and follow the wave pattern. If I start at the left and follow the wave, it doesn't matter which side I follow. If I go up, down, this is one wave. This is 2 waves. So I have 2.5 wavelengths here on the length of this string. So 2.5 is what, 5/2 wavelengths? And I can solve for the wavelength as being 2L over 5. If I relate that here, 2L over M, that means M has to be 5. So that's another way to reason this out. All right, one more concept question. What do you think about this? Okay, the correct answer is C. Okay, so originally we have M equals 2 because we have this 2 antinodes. So this is the second harmonic. By reducing the temperature, I'm tired, sorry. Reducing the tension to 1/4 of its original value, we know that's going to change the speed. The speed of the wave on the string is dependent on the tension. So if I am reducing our tension to 1/4 of what it was, if I bring out this square root of 1/4, this is going to be 1/2, and then this is the original speed. So the new speed is half of what it originally was. Now, to relate that back to frequency and wavelength, we know the speed of a wave is wavelength times frequency. They're telling us that the frequency is unchanged, the length of the string is unchanged, it's the same string, so mu is the same, frequency is the same. If the speed is cut in half, then the wavelength has to be cut in half as well. Well, the wavelength for a standing wave on a string is 2L over M. M is originally 2, but for the wavelength to be cut in half, so we have 1/2 of lambda 2, 1/2 of lambda 2 was when M was 2. So our new wavelength, we now have to say is 2L over 4. So M has to be 4, the fourth harmonic, if we cut the tension down to 1/4 of its original value. And so C is the option that has the fourth harmonic. It has the 4 antinodes.